Okay, hello everyone. Uh, our group is Group 10 from Computer Architecture, and today we will present about assembly language and do some coding exercises. And the outline of our presentation have three parts. The first part is about introduction of assembly language, and I will present this. The second part is basic structure, syntax, and logic of assembly. Lafayette will present this, and Kern will present the modern assembly application tools and thinking, and he will present the exercise of coding. The first part, introduction to assembly language. What is assembly language? Assembly is a low-level programming language that is closest to hardware. It serves as an intermediate language between machine code, or we can call it binary language, and high-level language like C, C++, and or Python. Each assembly language is specific to CPU architecture, such as it, it exists like Intel or AMD, ARM like Apple Silicon or one called Snapdragon, and MIPS. And for some example for this, the machine code like 1 0 1 1 0 0 0 0 1 1 0 0 0 0 1. It can convert to assembly code like MOV AL dot city1H. Okay, and the role of assembly in computer system. Assembly acts as a communication bridge between high-level software and low-level hardware. It translates human-readable instruction into machine-executable commands. And we have a table to compare assembly language versus the high-level programming language. We have some criteria like performance, control over hardware, readability, abstraction level, portability, operating system, driver, and firmware. Okay, about performance. Assembly language is very fast. It's faster than high-level language, and especially Python. Yeah, Python is executing code is very slow. And about control over hardware, the assembly is full control, but the high-level language is limited. About readability, assembly is hard to read, but high-level language is easy to understand, like Python. Python is similar to human language, yeah. And about the abstraction level, assembly is very low, but high-level language it have a high abstraction level. About portability, assembly is have a architecture specific, but high-level language it has a cross-platform. About operating system, drivers, firmware, assemblies can just do a loading like this, but high-level language can do something better, like web, apps, mobiles, AI, or anything else. And we have some advantages and disadvantages of assembly language. About advantages, assembly language is high performance and speed. This has direct control over hardware. It very efficiency memory uses, and is useful for debugging at machine level. It also essential for low-level system programming. About disadvantage, it's hard to learn and write. It's difficult to debug and maintain. It's portable across architecture, and the time consuming is very long for complex application. The finals is low abstraction and more error prone. The next part, Young will present.
All right, let's start with the basic structure and logic of assembly program. First, an assembly program is made of instruction, register, labels, and memories operation. Each line typically follow the format labels and then instruction, operand, and command. Labels are optional. Operand specify what are the instruction act on, and command help explain the code. Programs are organized into sections such as data for defining data, text for the main code, and BSS for utilized variables. Assembly instructions usually executed sequentially, unless they are redirected by jumps or branches. On the left, we have a simple example that prints hello to the screen. The message is defined in the data section. The text section contains a code that calls a system interrupt using the integer 0 times 80 to write the message to stand out. So we expect the output to say hello, but in this case there's a timeout error, likely due to the restricted unsupported environment running cycles. Now let's start it. Let's look at how assembly instructions are written and how they work. Okay. Each instruction typically follow this format: memory, operand plus comment. This is optional. The memoric is the name of the operation, and the operands are the value of the register involved. Some common instructions include MOV is transfer the data between register or between memory and register. ADD and SUV perform arithmetic operation. JMP perform an unconditional jump to another location in the code. CMP compare two values. JE, JNE, JG, and JL are conditional jumps based on the result of a previous comparison. Commands start with a semicolon, and they help describe what the instruction is doing. On the right, we see a simple example. MOV AX5 load the number 5 into register AX. MOV BX3 load 3 into the register BX. ADD AX and BX add the value into BX to AX, so AX become 8. Next, let's start about how to control flow work in assembly. Assembly use the jump instruction to control the flow of the execution. First, we have unconditional jumps. Using the JMP instruction, this simply jump to a label part of the code. No condition required. Then we have a conditional jump, which are used after comparison. For example, JE jump if equal and JNE jump if not equal. We also have a jump based on size. JG, JL, JGE, and JLE for greater, less than, or equal comparison. On the right, there's a branching example. The program compares the content of register AX and BX. If they are equal, the code jumps to equal label using JE. Otherwise, it jumps to N label using JMP. This is a simple way to implement if-else logic in assembly. Now, for loops, assembly use counter register like CX together with the loop instruction. At the bottom left, you can see the MOV CX3 set the loop counter. There. Then loop start repeat the block until CX reaches 0. And finally, to my next final slide. To finish this section, let's look at some common registers used in assembly. Registers are small, high-speed sorted location inside the CPU. They temporarily hold data during the execution, like kind of like a variable in high-level programming. Each register has a specific role and is used for different operations. Let's quickly go over the main ones. First is AX, called the accumulator, mainly used for arithmetic and data manipulation. Second is BX, the base register, often used for memory addressing. CX is the counter register, commonly used in loop and string operation. DX is the data register, often involved in input and output and larger arithmetic operation. SI and DI are used for string processing and memory indexing. SP and BP, these are for stack, using function calls and stack management. IP, the instruction pointer, which holds the address of the next instruction to execute. And finally, the flags, these store the status of or the result of an operation, like whether a comparison was true or false. And that is my final slide. The next will be presented by Cường.
So my name is Kương, and I'm going to present this last part and explaining to you the coding problem. So now let's talk about why assembly still matters today, even work dominated by a high-level program language. Um Here is some real-world application where assembly is either used directly or strongly influence the system design. First is the operating system kernel like Linux or Windows bootloader, where assembly is used during early startup state before the C code run. Um, it's also uh, used for device driver and firmware, where direct hardware access is required and timing is critical, and is used for embedded system such as microcontroller um, or IoT device. We have limited memory and needs extremely efficient code. It's also used in game engine and graphic programming, especially performing critical parts like rendering loops or physics engines. Reverse engineering and security research when you analyzing malware and vulnerabilities. Assembly is the language of the binary, and slot one is custom the compiler, debugger, and low-level tools. These need to interact closely with memory, register, and the CPU architecture. So now we'll take a look at the tool you need when working with assembly, whether you are writing a new code or analyzing the existing binaries. If you want to write assembly code, you will need an assembler, and here's are three of the most popular option. First is NASM or NetWise assembler is a widely used cross-platform assembler use Intel syntax with for Linux or Windows. MASM, Microsoft Macro Assembler, is a Windows-specific assembler maintained by Microsoft, common in Windows driver and kernel-level development. MUAO6 is a beginner-friendly emulator that can simulate the Intel AOA6 CPU. It comes with graphical interface, making it perfect for practicing and visualizing how the code execute. So assembly is also essential when reverse engineering binaries, for example, during malware analysis or security testing. Here's some powerful tool for this. First is 64 DGB or only DBG. Uh, it's a window-based debugger that lets you trace and step through binary code line by line. Mm, IDA Pro is a professional grade disassembler and engineering platform with a graphic user interface. Extremely powerful, but it's also expensive. Um, Vitra and is open source reverse engineering tool developed by the NSA. Is free, feature-rich, and a great alternative to IDEs. And Slack one is Radar 2 is a lightweight scriptable toolkit for advanced user. It's run in the terminal and extremely customizable. So now let's now shift from the tool to thinking. Specifically, how learning assembly shaped your mindset as a programmer. Mm, here's how assembly shaped your thinking. First, each improve your graph memory layout, including stack and heap. Since most developer only make us understand. It's for you to think basically, not think happen unless you tell the CPU exactly what to do. It make you better low level debugger. You will start recognizing crash pattern, uh, buffer overflow or register misuse just by reading the raw output. And you will also understand the performance bottleneck, where the circle or weighted, uh, where the memory thrashing occur. And finally, is make you stronger at using C++ building compiler or working with embedded system. Uh, uh, now we will um, now we have explored what assembly is, how it's work, and what it's good for. A natural question arises when you should actually use assembly language and when you should avoid it. You should consider using assembly in low level, performance critical or hardware dependent tasks such as writing operating system or bootloader, developing device driver or firmware, working with embedded system, uh, doing reverse engineering or security research, or optimizing performance critical code. On another hand, you should avoid assembly when you priorities are speed of development, maintainability, or portability, such as web or mobile apps or graphic user interface, large scale business, mm, logic system. When you do AI, machine learning, or data heavy application, uh, or when you need fast development and long term maintainability. And because assembly is hard to read and even harder to maintain, and portability is the key. Assembly is tightly coupled to CPU architecture. What work for on its ASIC won't work on ARM, for example. So uh, in the last part, I will um, show you guys the code for this problem, and I will walk through and explain it line by line. So The problem is writing an assembly program to divide the value in the AS register by the value in the BS register, store the quotient in the DX register, and the remainder in the AS register use the DIV or IDIV instruction. So let's walk through the code. In the first line and the second line, we beginning by setting the memory to decimal mode, which separate the code and data into different segments. The second line does stack 100 heads, set the aside 256 byte per stack, which we will use here, but it's good practice to define. So in the line 4, dot data, here we will normally define the variable or string, but since our program operate entirely on register, we don't use any data. We don't need any data section. So in the line 7 and line 8, the dot code directive begin with the code segment, and the main is our program entry point. In two next slide, 9 and 10, move AX25 and MOV AX25 and MOV BX4. We load the dividend value 25 into the AX register and the division value 4 into the DS register. There are two numbers we want to divide. Move to the next slide. 20 is OR. This slide is very important. The DIV instruction divide the value in this is by the sort operand. Here is this, so we must clear the this before division to avoid the garbage value or overflow. Next slide, 13, div is. So this slide will perform the division, divide ax by bx. The quotient is stored in ax, and the remainder will be stored in dx. In our symbol, is 25 divided by 4 is 6 with the remainder 1. So AS will equal to 6 and this equal to 1 after the instruction. So next slide, 19 say is CH3 is this. So the original instruction div put the quotient in the AS and the remainder in the DS, but our assignment wants to the quotient in the DS and the remainder in AS, so we use the SCH instruction to swap them. So go to the two next slide, 21 and 22. MOV AH for CH inch 21 heads. So this is a standard DOS interrupt to end the program cleanly. We place the 4C head into the A head register and call the interrupt 21 heads. We tell the DOS to terminate the program and return the control to the system. So and the last line 23, this line will end the main code. So this is the simple. This is the our solution for the problem. Writing by instant code. So So this is the end of our presentation. Thank you for listening.